Hi, this is the final presentation video of my Gsoc 2019 project with beagleboard.org. I've been working on providing an API for programming languages to control the BeagleBone PRUs instead of echoing into the sysfs files. Working. At its core, there is a press daemon which runs as a system service to serve PRU requests. A daemon is required so that the user will not have to deal with root permissions while running his program. The daemon loads the remote proc module and performs the tasks of loading the firmware, starting and stopping the PRU, passing RP messages, and debugging. This is done by using the sysfs files provided by the remote proc module. The requests are sent to the daemon over a Unix domain socket called pressd.soc in the tmp directory. The return value is also sent back to the user via the same socket. The C++ bindings are required to encapsulate the PRU and the PRU subsystem. It establishes a socket connection to send PRU requests to the daemon. Furthermore, if scripting languages are to be used, we can use the C++ bindings to generate wrapper code using Swig. Swig stands for Simplified Wrapper and Interface Generator. The interface files required for using Swig are provided in the GitHub repository. This is a high-level API specification of the C++ bindings. Installation. Now I'll be showing how to install and use the API. The kernel version I'm using is 4.14.71 and I'm using a fresh Debian image right now to demonstrate the installation process. The image I'm using can be found on the BeagleBoard website. This is what I'm using. A Debian package has been made to simplify the installation process. To download it, go to the releases page of the press bindings GitHub repository. There was a kernel oops issue in the first release of the project, which has been solved in the current release. So to download it, click on this link. Now copy the Debian file into your BeagleBoard. The second version. The second release, sorry. And now to install it, use sudo dpkg -i PRU API. So as you can see, the press daemon has been installed and is now running in the background. To check if the installation process is done correctly, cd into bin. These are two additional files that were added during the installation process. This is the firmware elf object file for an RP message loopback test, and this is the user space object file which uses the press daemon, the API, and loads this firmware into the PRU and starts the PRU. So if you do /userspace.o, it loads the firmware and now if you enter any message, the PRU echoes back. This ensures that the press daemon is installed correctly and that the press API kernel module is also installed correctly. The press API kernel module creates ARP message channels by the name of press API PRU1 for PRU1 and press API PRU0 for PRU0. Examples. The following examples were made during the project that demonstrate the use of the API. PWM generator generates custom PWM of given frequency and duty cycle up to 1 MHz. Stepper motor control to accurately control stepper motors using the above PWM generator at its base. Waveform generator to generate custom waveforms of up to 8 channels according to the wave samples provided by the user using RPMessage. And a debugging program was also made to peek into the contents of the PRU SRAM and DRAM and to view the PRU control and general purpose registers. Step motor control. This is a good example of how the user can focus on writing firmware instead of worrying about opening and closing the RPMessage and sysfs files. The driver library takes input degrees and revolutions per minute from the user and sends one command to the PRU1 and then waits until it gets a confirmation message back from the PRU1, after which it sends the next command. This ensures that a new command is not sent to the stepper motor while it is already active. The PRU1 does the job of taking the three 4-byte integer values as input and writes them to the PRU shared memory. The driver library then enables the PRU0, which reads the PRU shared memory and starts sending out the pulses which drives the stepper motor. After the number of pulses have been reached, it interrupts the PRU1. The PRU1 then sends a message done \n through the same RPMessage channel back to the ARM Linux so that the next command is sent and is carried out. To execute the other firmware examples, clone the press bindings repository. CD into examples, firmware examples. Now going to the code of 8-channel waveform generation. The wave samples are stored in arrays of size 101. The range of the sample value goes from 0 to 100, 0 representing minimum brightness and 100 representing maximum brightness. The value of the 101st element is always set to be 150 so that the assembly code running on the PRU side knows that all the sample values have been used up and that it needs to begin back from the first one. So the process is to first fill all the wave sampled values into the arrays. Next, send the total number of samples to the PRU1 and then finally send the sample data in raw form to the PRU1 in an interweaved manner. So after waveform 2 we send the sample value of waveform 3, after that waveform 4 and then repeat this on up to 800 values. On receiving these values, the PRU1 stores them into the PRU SRAM and the PRU0 reads these values from the SRAM and generates the 8-channel output. Do sudo make. This sets the pin marks, compiles the firmware for both of the PRUs, installs it, compiles the user space program and then runs it according to the values set. The top 6 are in phase with each other and have 1 Hz frequency. The bottom right one is out of phase by pi radians. The bottom left one is of twice the frequency than the other ones. I would like to thank my mentors Abhishek Kumar and Zubin Tulani for always helping me with the issues I faced. Without their help, this work wouldn't be possible. I would also like to thank Hunye Yao for explaining the PRU memory to me, Jason Kreidner and Kathy Wicks for helping me out on the IRC channel. Thank you.